Hello everyone, today I welcome all of you in my next online class, lecture 5. So today if we go forward, I'd like to revise the topics which we already covered in our previous classes. Heat and temperature, modes of heat transfer, conduction, convection and radiation, general heat conduction equation for solid geometry with heat generation and stay unsteady state, and then from there cylindrical coordinates and from spherical coordinates. Then we have discussed of heat transfer from slab. From slab we discussed about the heat transfer with no generation and steady state. Similarly, we will discuss today. We will start from cylinder. What is the amount of heat transfer if it's a one dimension and steady state? So here you see in this case one dimensional steady state and without heat generation and cylinder. So it's definitely the mode of heat transfer is conduction and the body is cylinder. So particularly for this already we have given the equation. So you see 1 by r2 r square delta 2t by del phi 2 plus delta 2t by del r2 plus 1 by r delta t del d by del r plus delta 2t by del z2 plus qg by k equals to 1 by alpha del d by del t into dt. Now if it's a one dimension, then I consider only r, on phi and z, both these dimensions I'll take it as 0. No heat generation means qg I'll take 0, and unsteady state steady state means I'll take del d by del t term is 0. So I can write here, I can reform the equations delta 2t by del r2 plus 1 by r delta t by del r equals to 0. Now in this particular cylinder, if I look at this diagram, see in this particular cylinder we have two radius. One is inner radius, another one is outer radius. So that particular cylinder or cylindrical pipe is having some thickness of thickness, and this is having some length. Okay, some length of L. Okay, some length of L is the length of cylinder, and cylinder has inner radius of R1 and outer radius of R2. Now at R1 radius the temperature is how much? T1. At R2 radius the temperature is how much? T2. Now you see, if I assume that temperature T1 is more than T2, then heat will be transferred from inside to outside. So I can write delta 2t by del r2 plus 1 by r delta t by del r equals to 0. Now in the next line, I'll just multiply with the r, so I can write r into d2t by dr2 plus dt by dr equals to 0. Now, if I want to integrate, so before integrating, I can write these equations in this like ddr of r into dtr, r into dt by dr equals to 0. Now if I integrate with respect to r, so integration of ddr of r into dt by dr equals to 0. So we get r into dt by dr equals to C1. Now how do you get this? So we have simplified here r into dt by dr equal, so we differentiate with respect to r, we get ddr of r into dt dr. So r into ddr of dt by dr plus dt dr into ddr of r. So here from here we get r into d2t by dr2 plus dt by dr. So from here if I integrate, we get, so r into dt by dr equals to C1, and next line if you can write dt equals to C1 into dr by r. Now what we will do, again we integrate. So if we integrate, so integration of dt equals to C1 into integration of dr by r. So integration of dt means t equals to C1 into ln of r plus C2, another one constant. So now you see C1 and C2 both are constant, depends on boundary conditions. So how do you generate the boundary conditions? So again you go back to the picture. So you see here at a particular inner radius R1 temperature is T1, and another one time at a particular radius R2 outer radius temperature is T2. So first if we put the first boundary conditions, we get here T1 equals to C1 into ln of R1 plus C2. And the second time again if we put in the second equations, second boundary conditions, then we get T2 equals to C1 into ln of R2 plus C2. So now if we solve these two equations, we want to find out the value of C1 and C2. So what do you do? 5 minus 6. So in the left hand side we get T1 minus T2. In the right hand side we get C1 into ln of R1 plus C2 minus within bracket C1 into ln of R2 plus C2. So T1 minus T2 equals to C1 into ln of R1 plus C2. If we remove the bracket, minus C1 into ln of R2 minus C2. So here we can write T1 minus T2 equals to C1 into ln of R1 minus C1 into ln of R2 plus C2 minus C2. So the C2 and C2 cancels out. So finally we get here T1 minus T2 equals to C1 into ln of R1 minus ln of R2. So we can write C1 into ln of R1 by R2. Now again we get the value of C1. So now we want the value of C2. So how do you get this? So put the value of C1 into that 5 equation. So what we will get? T1 equals to C1 into ln of R1 plus C2. So T1 equals to T1 minus T2 by ln of R1 by R2 into ln of R1 plus C2. So from here the value of C2 comes T1 minus T2 or T1 minus T2 into ln of R1 divided by ln of R1 by R2. So here if we put the value of C1 and C2 into the equation number 2, so we get T equals to C1 into ln of R1 R plus C2. So we get T equals to T1 minus T2 divided by ln of R1 by R2 into ln of R plus T1 minus T2 into ln of R1 divided by ln of R1 by R2. So we can rearrange and we can write T equals to T1 plus T1 minus T2 into ln of R divided by ln of R1 by R2 minus T1 minus T2 into ln of R1 by ln of R1 by R2. So this is my temperature distribution equation. So now again comes here this Fourier's law. So again we want to calculate the heat transfer. So Q equals to, you can write minus Ka dt by dx minus Ka dt by dr, because the now the dependent term is not x, dependent term is my radius, so that's why dt by dr. So from equation 1 we already calculated r into dt by dr equals to C1. So dt by dr equals to, you can write C1 divided by r. Now C1 value we know, so you replace the value of C1. So dt by dr equals to T1 minus T2 by ln of R1 by R2 into 1 by r. So from Fourier's law finally we calculate minus Ka into dt by dr minus Ka into T1 minus T2 by ln of R1 by R2 divided into 1 by r. So from here area of cylinder we know the formula 2 pi RL, where this L is the length of cylinder. So if we replace the value, so Q equals to 2 pi RL into T1 minus T2 by ln of R1 by R2 into 1 by r. So RR cancels out, we can finally get minus 2 pi KL T1 minus T2 by ln of R1 by R2. Next, in this minus, if we keep it in the down, ln of R1 by R2, so there if we put the minus, then we get heat transfer Q equals to 2 pi KL T1 minus T2 by ln of R2 by R1. So this is the amount of heat transfer through cylinder from one dimension, no heat generation and steady state. So today this is much. This much, then I'd love to finish the class. So before finishing, again recall the whatever we studied. We studied about slab, the slab heat transfer. If it's one dimension, then formula is Q equals to Ka into A into T1 minus T2 by L. And for cylinder, the formula of cylinder is Q equals to 2 pi KL T1 minus T2 by ln of R2 by R1. Okay, thank you.